basically the goal of this session is to go through chapter 2 together. And in this chapter, what we're going to be doing is diving into the sort of internals of the Transformers library. And in particular, we're going to be looking at the sort of models. So there's a set of model APIs that we're going to look at, and also the tokenizers, which we relied on heavily to convert text into a format that the models can process. And so you've seen in the first lessons that we have a pipeline API. And this pipeline API basically wraps all of the complexity of pre-processing and post-processing text and also feeding it to the model so that you just have to basically give it a sentence and then you could classify, for example, the sentiment. And today we just want to sort of unpack what's happening inside this, this function, and also to understand some of the different sort of approaches you can take for tokenizing your text, and also how to save and load the models and tokenizers. And we'll finish by looking at what you have to kind of do when you're dealing with sentences or text that have different lengths, because it turns out that in PyTorch and TensorFlow and most deep learning frameworks, we need a kind of standardized sort of rectangular input for our models. And basically the way we're going to do this is I'm going to go through the sections and then pause for questions. But in the meantime, if you have some sort of very urgent thing that you want to ask, Omar will be here helping us with guidance. So just to give you a taste of like what's we're going to be sort of covering, but at a higher level, every single model in the Transformers library has a corresponding modeling file. So for example, here, what I'm looking at is the modeling file for BERT. And this file has all of the source code for all of the different tasks that you can use BERT for. So for example, if I look for BERT model, this is the sort of base class that we're going to be looking at today, which is responsible for basically creating contextualized embeddings of the inputs. So how do we create kind of numerical representations of our text that have some sense of meaning? And this kind of class is relatively simple. It just has the embedding layer, which you saw in the first chapter. So the thing that we passed through before we hit the transformer stack. And then we have an encoder. And this encoder is essentially responsible for converting these tokens or these token embeddings into these contextualized representations. And I just recommend as sort of like your homework, have a look through some of this code. So any sort of class that you see us using today, for example, BERT model, have a look at the sort of source code. And this really helps you understand how transformers work. And at least for me personally, it was only by sort of going through this kind of step by step and understanding how all the inputs go through the forward pass that I was really able to understand all the inner workings of a transformer. So that's just a little side note. So to get started, maybe let's have a look at what really happens behind the pipeline. So let's kickstart with this video.
What happens inside the pipeline function? In this video, we'll look at what actually happens when we use the pipeline function of the Transformers library. More specifically, we'll look at the sentiment analysis pipeline and how it went from the two following sentences to the positive and negative labels with their respective scores. As we've seen in the pipeline presentation, there are three stages in the pipeline. First, we convert the raw text to numbers the model can make sense of using a tokenizer. Then, those numbers go through the model, which outputs logits. Finally, the post-processing steps transform those logits into labels and scores. Let's look in details at those three steps and how to replicate them using the Transformers library, beginning with the first stage, tokenization. The tokenization process has several steps. First, the text is split into small chunks called tokens. They can be words, part of words, or punctuation symbols. Then, the tokenizer will add some special tokens if the model expects them. Here, the model used expects a CLS token at the beginning and a SEP token at the end of the sentence to classify. Lastly, the tokenizer matches each token to its unique ID in the vocabulary of the pre-trained model. To load such a tokenizer, the Transformers library provides the Auto-Tokenizer API. The most important method of this class is FromPretrained, which will download and cache the configuration and the vocabulary associated to a given checkpoint. Here, the checkpoint used by default for the sentiment analysis pipeline is Distilbert based on case fine-tuned SSS2 English, which is a bit of a mouthful. We instantiate a tokenizer associated with that checkpoint, then feed it to the two sentences. Since the two sentences are not of the same size, we'll need to pad the shortest one to be able to build an array. This is done by the tokenizer with the option padding equal true. With truncation equal true, we ensure that any sentence longer than the maximum the model can handle is truncated. Lastly, the return tensors option tells the tokenizer to return a PyTorch tensor. Looking at the result, we see we have a dictionary with two keys. Input IDs contains the IDs of both sentences, with 0 where the padding is applied. The second key, attention mask, indicates where padding has been applied, so the model does not pay attention to it. This is all what is inside the tokenization step. Now let's have a look at the second step, the model. As for the tokenizer, there is an AutoModel API with a FromPretrained method. It will download and cache the configuration of the model, as well as the pretrained weights. However, the AutoModel API will only instantiate the body of the model, that is, the part of the model that is left once the pretraining head is removed. It will output a high-dimensional tensor that is a representation of the sentences passed, but which is not directly useful for our classification problem. Here, the tensor has two sentences, each of 16 tokens, and the last dimension is the hidden size of our model, 768. To get an output link to our classification problem, we need to use the AutoModel for sequence classification class. It works exactly as the AutoModel class, except that it will build a model with a classification head. There is one auto class for each common NLP task in the Transformers library. Here, after giving our model the two sentences, we get a tensor of size 2 by 2, one result for each sentence and for each possible label. Those outputs are not probabilities yet. We can see they don't sum to 1. This is because each model of the Transformers library returns logits. To make sense of those logits, we need to dig into the third and last step of the pipeline, post-processing. To convert logits into probabilities, we need to apply a softmax layers to them. As we can see, this transforms them into a positive number that sum up to 1. The last step is to know which of those correspond to the positive or the negative label. This is given by the ID to label field of the model config. The first probabilities, index 0, correspond to the negative label, and the seconds, index 1, correspond to the positive label. This is how our classifier built with the pipeline function picked those labels and computed those scores. Now that you know how each step works, you can easily tweak them to your needs.
So, let's see. All right. So, do we have any questions at this stage about the pipeline? So, one of the things that we saw is that there's these kind of 3 components. There's like a pre-processing stage. Okay, great. Okay, great. So one of the first questions we have is, could you please explain the intuition behind the BERT SST2 English checkpoint? And what are the different flavors of checkpoints to be used? And how did we choose SST2? Okay, great. So basically, each of the transformer models, they have a sort of pre-trained base or pre-trained backbone, which I think you saw in the first chapter. And then what we do typically with models like BERT and GPT is we fine-tune them on a downstream task. So the idea is that you take, for example, BERT, which was pre-trained on Wikipedia and the book corpus, and then you say, okay, I want to do classification now. So I'm going to basically take these weights that I had in my original model, and I'm going to add a classification head, which is going to just basically be a linear layer that allows us to do the classification task. And then we do the fine-tuning step on a particular task. So if you want to understand a little bit about how the the models work, or the description of the models. If we look at BERT, and what was this guy called? This is BERT uncased, fine-tuned. So uncased, fine-tuned, and then it's SS, what was it? Fine-tuned, DistillBERT, okay. DistillBERT, uncased, fine-tuned, what am I missing here? Base. DistillBERT, base, uncased, fine-tuned, okay. So if we look at this, then what we can see is that this is a checkpoint that was fine-tuned on a particular task. So this task here is called the tree bank task, the binary classification benchmark. And I think from memory, this is just like a sentiment analysis task, which just has label or data given in terms of just two labels, like, positive or negative. So the basic idea of like, why did we choose this? Or the basic answer is that we were just trying to sort of demonstrate how the pipeline works for sentiment analysis. And this is one model which is well suited for that task. So I hope that answers your question, DK Crazy Div. And then the other question we have is, in this case, we assume that there are only two classes for classification. How do we specify a multi-class problem, and what checkpoint would you use? Okay, great. That's a very good question. So maybe what we can do is let's have a look at the collab for this chapter. So here we've got a sentiment analysis pipeline. And of course, it's just going to predict two classes. And so now I'm just going to instantiate the tokenizer, and here's the model. Okay, so if we look at a model, every single model has a config, and this config tells you things, for example, like the number of classes. So you can see we've got two classes here. And what you can do when you instantiate a model, you can define the number of classes you would like when you instantiate the thing for text classification. So just to give you an example, let's suppose that I take a checkpoint for multi-class. Now I'm going to do two things here. I'm going to show you first, how do we instantiate a model that we then would fine tune ourselves. And then I'll show you the sort of simpler case where we have an existing pre-trained model. So if I don't have, imagine I just have my own data set and there's no model on the hub that is suitable for what I want to do. What I might do is I'll say, okay, I'm going to take DistillBERT base uncased. And this is just the pre-trained model. There's nothing sort of special about it. I still have to do some work. And then what I could do is I can say, okay, I'm going to take, first I need to take from transformers. I'm going to import an auto model, but now I'm going to do it for sequence classification. So this is where anytime you're dealing with like text classification or multi-class, multi-label, these things, this is a sequence classification task. And then what I'm going to do, I'm going to take my model for sequence classification, and then I can do my usual from pre-trained. And I take my checkpoint that I've got now, this new one. And then what I can do, I can pass keyword arguments that will specify how many labels I'm dealing with. So imagine that my data set has 6 classes that I'm dealing with. So what I can do is I can say the number of labels is 6. And now what will happen, it will download the base model or the pre-trained model for DistillBERT, and it will then add a classification head on top of this model, and it will configure it with the right number of classes so that we can do fine tuning appropriately. So now if we look at our config, you can see that it's already initialized the model with 6 different classes. And we don't know the labels yet because we haven't provided our own data set and our own labeling convention, but we could do that. And then from here, we could then just fine tune and train the model exactly as we've done, or we will do in the next chapter. So that's one way of doing it. Now, the other part of the question is, how do I take a sort of pre-trained model or fine-tuned model from the hub? And this is a little trickier to figure out like, which model is suitable for your task. So the way I usually do it is I look, for example, at text classification. So I do a filter here on text classification. And then I sort of like ask myself, okay, maybe I'm dealing with, let's see. Now this isn't so easy to find a multi-class example. So I think in general, yeah, so actually finding the multi-class model that is suitable for your task takes a bit of work. I mean, maybe Omar already knows a fast way to get this, but generally speaking, all of the models that we have here are in some sense fine-tuned on a task. So for example, like this German sentiment BERT presumably is 2 classes. And one way you could quickly check that is by looking at the files and versions and seeing in the configuration how many labels you have. So in this case, there's 3 labels. But actually searching for this effectively on the hub, I'm not sure. Maybe there's a way of doing this. Or maybe this is a good feature we should add in the hub. So I am Holmes. I hope that sort of partially answers your question. But if not, then feel free to write in the chat. Yeah, exactly. We should add a feature for this. It's great. We basically, I think what we would like is a filter where we could filter between binary classification, multi-class, and multi-label, and then that would allow us to refine things. But good questions. Awesome. Okay, so are there any more questions about the pipelines before we look a bit more at the code? Okay, so in that case, let's have a sort of walk through this this collab with the pipeline to sort of get a deeper understanding of what's going on. So we've got this example here where we're basically downloading the sentiment analysis pipeline, and we've got now the classifier which we can feed these 2 texts that you saw in one of the earlier chapters. But now what we want to do is we want to understand what really is happening under the hood. So remember that the first thing we need to do is we need to process or pre-process these raw texts, because basically all neural networks can't do operations on raw text. It's kind of like, imagine you want to do like matrix multiplication. How do you do that on like a string? And so what we can do instead is we use a tokenizer. And one of the key things that you should remember is that if you're doing any sort of fine tuning or any like sort of inference or predictions, it's really important that the checkpoint you use here is the same for the tokenizer and the model. And that's because when these transformers are pre-trained on a large corpus, there's a corresponding tokenizer that was also trained in some sense to learn the vocabulary of that corpus. And so if you sort of mix and match a checkpoint for one tokenizer and then a different checkpoint for the model, basically you'll get a mismatch in the vocabulary, and then you'll get kind of garbage in your outputs. So that's one sort of thing to watch out for. Okay, so we've got a tokenizer, and now we've got these same raw inputs. And if we basically feed these 2 sentences into the tokenizer, you get, generally there are 2 things that you just sort of need to remember. You're going to get something called input IDs. And these input IDs are basically a mapping of every single token in our sequence to a unique number, or a unique integer to be precise. And this is basically a mapping in the vocabulary. So imagine that I was thinking about, like, I don't know, the whole English language where I'm just dealing with words. Then I'm going to have probably several 100,000 words or tokens in my vocabulary. And then if I get like the word whole, I would like to be able to match that to a number that corresponds to this mapping in the vocabulary. But as we saw, I think in the first chapter, or in fact, we might see it as well today, this kind of like tokenization in terms of words is not very efficient. And so what we usually do is something a bit cleverer. But the basic idea is that every single token in this input is going to be mapped to a number. And then those numbers allow us to sort of distinguish between different tokens in the sequence. So that's what input IDs are. And the other thing that you're going to see today in more detail is something called an attention mask. and I'll explain a bit more later on what this is really doing, but you can already see that it's kind of putting a bunch of ones at some part of the sequence and a bunch of zeros towards the end of the sequence, and this will become clearer later on. Okay, so we've got the tokenizer. So we've now converted our raw text into these IDs, or these numbers we can operate on. And then let me just make sure I load the correct checkpoint here. So now we're going to load the model. So this is the thing that will process these inputs. And let me just delete this. Okay, and so then the question is, how do you feed your inputs to your model? So the simplest way is to just take this dictionary that we have here, which has two keys. It has input IDs and attention mask. And then we can just use the standard Python unpacking operator to just feed all of the keys and values to the model. And when we do this, this will basically feed the inputs to the forward pass of the model to generate the outputs. And so one way we could look at that, I think we can probably do this. If we look at the forward, you can see here in the Colab, it's showing us basically what the arguments this forward pass can accept. So it tells us we can accept input IDs, we can have an attention mask, and then there are like some more kind of sophisticated or advanced things we could also provide. But we don't need to do them for today, but just so you know, there are other things that you can do. So you can see that, okay, we need to provide at least these input IDs and attention mask. And so when we do the unpacking, like here, this will basically run through the forward pass and produce some outputs. And as we saw in the video, these outputs are basically called like hidden states. And these hidden states are just some sort of like say compressed representation of the text. So we're taking this raw text, we're converting it first into numbers, and then we're taking those numbers, and then we're converting those sort of integers into dense vectors. So basically every token is now associated with a vector. And in this case, we've got 16 vectors per sentence, and each vector has 768 dimensions. And that's just because of the way BERT was, or DistilBERT as well, was pre-trained. So let's have a look at one of these vectors. So we've got outputs. So I'm going to take the first sentence, so that's the first index, and I'm going to look at the first token of this sentence. And so if you look at this, they must be slices or integers. Okay, because I need to do last hidden state. Okay, good. So actually, let's just take one step back. If we just look at the raw outputs, you can see that in transformers, all the outputs from the models are usually wrapped in an object, which is kind of something we can then index by attribute name. And so here we've got something called the base model output. And then this has, in this case, just a single attribute called the last hidden state and the tensor. So if I want to then access this last hidden state, now I've got a tensor, which has the thing I wanted to do. So I'm going to get the first sentence. I'm going to get the first vector or the first token, sorry, the vector corresponding to the first token. And this is now this, huge thing of, numbers from, negative to positive. And this should have a size of 768. Where are we? Yep. So this is basically the numerical representation of the first token in the first sequence or the first sentence we passed. Okay, so let's just check, are there any questions? Okay, cool, so let's carry on. Okay, so this is basically what the numerical representations are produced by the model. And then, as we saw in the video, these numerical representations by themselves, they don't let us do things like text classification. They just say the numerical representation of this token is blah. And now if we want to do classification, we need to take that vector or these feature vectors, and then we need to add them or combine them with a classification head. And so the whole transformer library is built around this idea of taking a model for task X. And task X can be things like sequence classification, question answering, summarization, translation, so on and so forth. And in this case, when we instantiate a model with sequence classification, as we saw before, this is now going to create a model which has a number of labels. So you can see here, we've now got a model with 2 labels because that's what this pre-trained checkpoint has. And then when we look at the outputs, we've now got, instead of having just these last hidden states, we've got logits. And these logits are basically what happens when you feed these feature vectors through this linear layer. This will now compress these 768 dimensional vectors into just 2 numbers, or project them into 2 numbers. And these are the things that we can then use to derive probabilities and figure out, for example, which class is the most likely. So you can see here that this one here is more likely than this one, and vice versa, because I think the second example is like a negative sentiment. Okay, so that's more or less how we think about the outputs from a model versus a model with a classification head. And here what we can see is if we want to convert our logits into probabilities, we can just take a softmax over them. And you may remember that a softmax basically takes all of the inputs, it exponentiates them, and then it normalizes that exponential by the sum of all the exponentials. So you basically end up having something that ranges from 0 to 1. So it's a good candidate for a probability. And if we do that, we then get now probabilities for each of the 2 sentiments. And also we now can see this is the way we can map between the label ID, which says, what does 0 mean, in terms of something that's a bit more meaningful. Okay, so let's have a look. Let's see. Okay, great. So we have a question from SRM Sumya, which says the classification model should take the output from the Distilbert model. That's exactly right. So in fact, let's have a look at this. If we look at class, I'm doing this for BERT, but it's the same for Distilbert. So if we take BERT model for, where is it, for sequence classification. So if you look at what this model actually has, it has the BERT model that we saw, or the Distilbert model we saw in our example, and then it just applies dropout and a linear layer. And the linear layer has a dimension of the hidden size, so the 768, and then it's going to compress that into just these 2 numbers defined by the number of labels. And so if we look down at what happens inside the forward pass, the first thing we do is we get the outputs from the BERT model. So these are just the feature vectors, these 768 dimensional vectors. And then you can skip most of this kind of stuff. The main point is that here we, well, don't worry about the pulled output. The main thing is that we feed these outputs into the classification head to produce the logits. So it's a great question. Okay, so we've got a question from Platon Shiba. So how can we see what the token representation means in the text? So cool. So maybe just to show you like something that, let's see, maybe we get ahead of ourselves, but that's okay. Okay, so we've got these raw inputs, which are given by these strings, and then we get these input IDs like this, right? And so one thing we could do, if you want to go backwards, and we're going to see this later, but what I could do, I can say, okay, tokenizer, and I'm going to decode. So I'm going to do the opposite of what I did before. And now I'm going to take my input IDs and fingers crossed, this, I need to do input IDs. And now you can see by using this decode method, we're able to kind of reverse the process of the raw text. But what it does is it also introduces some special tokens. One is called the CLS token, which kind of just tells you this is like the start of the sentence. And then we have a SEP token, which basically is used to distinguish between pairs of sentences. So this is one way you can go back from where you started. And yeah, if you have more questions, we can tackle them as we go ahead. Okay, cool. So that's the sort of first look at how the pipeline works under the hood. So now what we could do is let's have a look at like the models in more detail. So I'm going to start by watching this video, and then we'll pause for questions, and then again look at some code.
How to instantiate a transformers model. In this video, we'll look at how we can create and use a model from the transformers library. As we've seen before, the AutoModel class allows you to instantiate a pre-trained model from any checkpoint on the Hugging Face hub. It will pick the right model class from the library to instantiate the proper architecture and load the weights of the pre-trained model inside. As we can see, when given a BERT checkpoint, we end up with a BERT model, and similarly for GPT-2 or BART. Behind the scenes, this API can take the name of a checkpoint on the hub, in which case it will download and cache the configuration file as well as the model weights file. We can also specify the path to a local folder that contains a valid configuration file and a model weights file. To instantiate the pre-trained model, the AutoModel API will first open the configuration file to look at the configuration class that should be used. The configuration class depends on the type of the model, BERT, GPT-2, or BART, for instance. Once it has a proper configuration class, it can instantiate that configuration, which is a blueprint to know how to create the model. It also uses this configuration class to find the proper model class, which is then combined with the loaded configuration to load the model. This model is not yet a pre-trained model, as it has just been initialized with random weights. The last step is to load the weights from the model file inside this model. To easily load the configuration of a model from any checkpoint or a folder containing the configuration file, we can use the AutoConfig class. Like the AutoModel class, it will pick the right configuration class from the library. We can also use a specific class corresponding to a checkpoint, but we'll need to change the code each time we want to try a different model architecture. As we said before, the configuration of a model is a blueprint that contains all the information necessary to create the model architecture. For instance, the BERT model associated with the BERT base case checkpoint has 12 layers, a hidden size of 768, and a vocabulary size of 28,996. Once we have the configuration, we can create a model that has the same architecture as our checkpoint, but is randomly initialized. We can then train it from scratch like any PyTorch model. We can also change any part of the configuration by using keyword arguments. The second snippet of code instantiates a randomly initialized BERT model with 10 layers instead of 12. Saving a model once it's trained or fine-tuned is very easy. We just have to use the save pretrain method. Here, the model will be saved in a folder named myBERTModel inside the current working directory. Such a model can then be reloaded using the fromPretrain method. To learn how to easily upload this model to the hub, check out the Push to Hub video.
So, any questions so far about the model, like loading and saving models, before we dive into some code? So, just to sort of summarize what we saw in the video, whenever we do this from pre-trained method with the model, we first need to get a config, and we saw that config just a couple of minutes ago. It defines things like the mapping of the labels to the IDs and how many labels the model has and all that kind of stuff, how many layers, all those things. And then that config is then used to load the weights of the model so that it makes sure that everything is kind of configured in the right way. And then once we have this model, we can then save it and then use it for other things. So if there's no kind of urgent questions right now, I'll have a look at the model's code. Just as a mention, you can watch these videos in your own time and work through this kind of text, but I think it might be sort of more useful if we just have a look at the code. So let's just check I can run transformers. Okay, so one thing maybe to mention is a really common example or situation that you will find yourself in is you basically, you've trained a model and now you want to share it in some way. And the sharing, typically, at least when I was working in my previous company, it was much more about deploying this model so that you could serve it or produce predictions that other services could consume. And so once you've saved your model, the question is like, okay, what the hell do I do with this thing? And as we can see here, this save thing will basically save two objects. It will save a configuration JSON file, and it will also save a PyTorch model.bin file. And this is something in PyTorch called a state dictionary, which basically provides all the information for the layers and the weights. And so if we want to use this in like to produce predictions, the first thing we need to do is what we've always been doing is we take some input text, we convert it into input IDs, and then we need to convert those input IDs into tensors, which we can then feed to the model. And so previously what we were doing was using like the tokenizer, and that's exactly what you would also do in practice. But in this example, we're just showing the outputs of the tokenizer. So let's have a look at what that looks like in code. So let's check if there's any questions. Okay, so maybe just to quickly summarize, we've got, you can also load your configurations using two different things. You can either load your model directly from one of the default configs in the library, and then this will provide you with like, a kind of summary about the hidden size and so on. But if you do this, the model is completely randomly initialized, which means all the weights are just random. And this model is going to just be garbage. It's not going to help you make any good predictions. And this is what you do actually when you want to pre-train a model, or you want to really train a model from scratch. So in practice, most of the time, what you're really doing is using the from pre-trained, and then this will initialize the model with the pre-trained weights and the correct head if we need it. So if we wanted to do, say, predictions, let me just instantiate this. So let's suppose that I've got my model and I'm happy with it. And so I want to save it so I can deploy it somewhere. So let's just wait for this model to download. Okay, good. So then what I could do is I could save my model, and this is just some path on your machine. So if we now look inside the file system, we can see that we've got a directory called directory on my computer. So now if I have a look at what's inside that directory, I've got these two files. I've got this config.json, and I've got this like binary file called PyTorch model. And so what we can do now is we can take that folder and we can, wrap it up, zip it up, put it on a machine. And then if we want to get new predictions, then what we do is we take our tokenized inputs, we then feed those or convert them into a tensor, because all the PyTorch models expect torch tensors. And so if we look at this model inputs, it's just going to be a tensor. And then we feed these inputs to the model. And then this is now what would constitute a prediction. And then you can, do whatever you want with that prediction. Maybe use it to make some sort of decisions, or maybe use it to feed a dashboard. Basically, the sky's the limit. And that's more or less like sort of, how you generate predictions. It's pretty straightforward. So let's have a look. We've got a question here. Out of interest, how long would it take to train BERT from scratch? And can you do it on Colab? Okay, so I think it really depends on the size of the corpus that you want to use. So for example, BERT was trained, if I'm not mistaken, on all of English Wikipedia, and a corpus called the books corpus, which is sort of scanned library books. And I think, let me think. So, let's do something like this. Why don't we find the answer? So on the fly, because I don't remember off the top of my head how long it took them to do it. And there's nothing better than live reading papers. Okay, so here's the BERT paper. And let's have a look at, I'm guessing they use TPUs. Okay, so they say here that they trained BERT base on 4 cloud TPUs. So this is 16 TPU chips, and each pre-training took 4 days to complete. So I think from memory, the cloud TPUs you get on Colab are just 1 TPU chip. So sort of roughly speaking, it would take you maybe 16 times 4, so 64 days to train on Colab, you know, with the same corpus. But I don't think so. Yeah, I'm not sure if there's a quick BERT training. However, I will show you something. There's a blog post by Hugging Face. Let's see, on training a model on Esperanto. So I'll chuck this in the chat. So can I do that? Okay, so this blog post, it uses a slightly older API, but the basic idea is to show you that you actually can train in a collab a BERT model as long as your corpus isn't too big. So this is Esperanto, which is a special language that is, has much less text than English. But I think from memory, this was trained in just an hour and a half, maybe a few hours. So let's see. Okay, maybe we don't see it here. We just have to look at the collab. Let's see. So the training of this model. Okay. So yeah, this training took almost 3 hours. So it really kind of depends on the size of your corpus. So in principle, you can, but if you want to do something that's like, say, as powerful as BERT, then you're going to need some more serious hardware. Okay. So there's another question by I Am Holmes. I understand that transfer learning or using a pre-trained model is the way to go instead. Yes, that's exactly right. So the sort of real power of like transformers and NLP sort of nowadays in general is that we don't really want to do pre-training ourselves because again, it's expensive and time and takes a long time. So I would almost always use a pre-trained model if I can. The only time you might really be stuck is if you're dealing with like a domain that's very different from any pre-trained model that exists. So for example, suppose I was trying to train a model on like source code. So, in the early days of transformers, there weren't any pre-trained models on source code, like, trying to, for example, understand Python, the language. And so then, using BERT base, like on English, and then trying to transfer it to source code might be a bit tricky. It might not give you very good results. And so if you, trained on a source code corpus, that would give you better results. And the other example where you generally need to find an alternative is if you're dealing with like a language that is not one of the sort of commonly supported ones. So my understanding is that there's like many languages, for example, in Africa, which aren't really represented highly in Wikipedia. And so then this is hard for people to train models or train transformers on. And then you typically need to do some sort of tricks to like take something that is like multilingual, like a multilingual version of BERT, and try to somehow adapt it to your language. But these are generally more advanced things that we can talk about later. Okay, so let's see. So where were we? We have looked at how we can. Another question. Can we change the config parameters of a pre-trained model and use it? Yes, but with some caveats. So, for example, let's think about what can we change and what can't we change. So, I want to make sure I don't say something silly. So let's have a look at the model config we have here. So this is the config associated with BERT base. And here you can see that there's a bunch of hyperparameters that were associated with the pre-training of this model. So for example, let's see. So I have a suspicion that if we change many of these things, we're going to break the model in a non-trivial way. However, let me think. What happens if we change the number of hidden layers? So you know what? Let's try. The usual way of doing things in deep learning is just to try. So I'm going to try to change. So BERT has a number of attention heads. So I'm going to see what happens if I reduce the number of attention heads from 12 to 6. Let's see if this works. So let's have a look at the config to make sure that worked. So now we've got attention heads 6. Now, what happens if we try to feed some inputs to this model? Okay, so interesting. Okay, so it seems that we can change the config and things work in the sense that we don't get errors. But I have a suspicion that like hacking into this in a pre-trained model would affect the kind of performance in some non-trivial way. Because if we think about like what happens when we do something like text classification, we're taking the whole like base model of BERT and then we're just stacking on top of this the classification head. And if I start kind of like, you know, doing an like dissecting BERT into pieces or something, you know, reducing the attention heads or changing the number of transformer layers. So BERT has 12 encoder layers. I have a suspicion that I would probably have some sort of non-trivial or negative impact on the downstream task like classification that I want to fine tune on. But maybe Omar has a different insight here. Okay, so that's a good question. I've actually never hacked into a pre-trained model this way. You know, maybe you could try and see like do some experiments like what happens if I completely change the number of layers, the number of attention heads in BERT and try to do classification, like sentiment analysis. Do I get better or worse performance? I have a feeling it will be worse, but it'd be a cool thing to check. And if you do check, please share it on the forums. Okay, so that was the look at sort of how we generate predictions. Let's now have a look at the tokenizers in more detail. So let's cross our fingers that the internet still works. Okay.
In the next few videos, we'll take a look at the tokenizers. In natural language processing, most of the data that we handle consists of raw text. However, machine learning models cannot read or understand text in its raw form. They can only work with numbers. So the tokenizer's objective will be to translate the text into numbers. There are several possible approaches to this conversion, and the objective is to find the most meaningful representation. We'll take a look at 3 distinct tokenization algorithms. We compare them one-to-one, so we recommend you take a look at the videos in the following order. First, word-based, followed by character-based, and finally, subword-based.
Okay, so let's get out of this. Okay, so that was like a high-level overview of what we've been talking about, that there's this general process we have to go through of converting text into numbers. There's a bunch of videos in this section that you can look at, which show the different types of ways you can tokenize text. Can you guys see me or not? Can you? Okay, good, great. All good. Yeah, the joys of home office. Okay, so what I was saying is there are different approaches or strategies you can take for tokenizing text, and the advantages and disadvantages of them just depend on the application you're interested in. So I'm not going to go through the videos, you can watch these yourselves, but let's just have a quick look at the sort of three most popular approaches. So the sort of first thing I might imagine is if I've got like a text like Jim Henson was a puppeteer, then what I might do is say, okay, I just want to split this text into words. And in English, a simple like trick to do that is just to split on white space. So most of the time in English, if there's a white space, that's the boundary between words. And then this would convert, for example, Jim Henson was a puppeteer into these 5 tokens. So in this case, a word is a token. But there are like several languages where this is like a terrible idea. So for example, if you have ever learned Japanese, you have characters called kanji, and these kanji don't have any words, any space. It's just a sequence of kanji, and in general, they're actually not even written from left to right. They're written from top to bottom. So doing this kind of splitting or tokenization in terms of white space just wouldn't work. And so an alternative approach is to try something called character-based. So this would be like, imagine you just split every letter in an English sequence into its own token. And this would actually be then quite good for Japanese, because every character is a kanji character, which then, you know, we could represent with a token. And so the kind of thing you can see here is that it really, the sort of tokenization strategy seems to really depend on the language that we're studying. And so the thing that like a lot of research has gone into is trying to find something that gives you like a good trade-off between these two kind of extremes of word tokenization and character tokenization. And maybe I should also mention a couple of drawbacks before we go into that. So one of the drawbacks with word tokenization is that this will create a vocabulary which is the size of the number of words in our language. So basically, if we have, imagine we just tokenize English, then we will need a token for every single word in the English language. And this is generally huge. It's going to be several 100,000 tokens, which makes it very like computationally expensive. But the other thing that's kind of not great about this is that it doesn't make any sort of distinction between like I don't know, dog and dogs, which are kind of like, you know, similar words, and we're kind of representing them now with 2 independent tokens. So that's the drawback with the word ones. And the character-based ones have the drawback that the model has to basically learn what a word actually means, because the only thing it gets now are characters, or it gets character tokens. And then it has to figure out over training that, okay, if I put together these characters in this order, this seems to represent like a more abstract object, like a word. And so this, at least for English, would be not a great strategy. So most tokenizers, they use something called subword tokenization. And the basic idea is that instead of like just splitting on word boundaries or on characters, you basically split, or you decompose a word into subwords. And an example here is like, let's take the word annoyingly. So annoyingly can be represented as maybe 2 subwords, annoying and ly. And then what we can do is we can just kind of collect the frequencies of these subwords and then use this to figure out basically what are like the most frequent subwords in the language, and then we can use those subwords to build back the full word itself. So if you know that you've got annoying and ly, you can then reconstruct annoyingly from these two components. And so, like, I guess there's an example here. You can sort of split let's do tokenization into these subwords. So that you can see this is kind of a mix of a word, token, with a subword, ization. And we've also got the exclamation mark being treated as its own separate token. And the sort of most common tokenizers that you would see, oh, there's a good question, I'll get to that, are things called word piece, which is the one that Bert used, or sentence piece, which is the one that GPT and the GPT models typically use. So there's a really good question. How do you design the subword boundaries? Is it manual? So this is more or less determined by the algorithm that you choose to use. And I think, like, in general, it's a mix of like manual rules and also learning, a form of learning from the corpus. So let's have a quick look at, let's see, I think it's the sentence piece paper. So this is, I'm going to put this in the chat. Okay, so this is one of the most famous papers on tokenization. And let's have a quick look at, so how are these boundaries? Okay. Yeah, that's right. So that's what I remember from this paper. So they say that historically, most like tokenization algorithms, they used manual rules. And the problem with this, of course, is that for every language you need your own set of rules, and it's a real like pain to sort of maintain and extend. And so, if I'm not mistaken, sentence piece is kind of like a learned tokenizer. So you actually have like a sort of optimization objective, and then you train this like you train a model. And so by training this on your corpus, you actually learn the word boundaries. But I haven't read this for a few years, and I might be forgetting something. But yeah, that's a good question, and I think maybe something that we can add in a future version of the course. Okay, so where were we? So we were looking at these different tokenization strategies. So let's maybe look at the Colab. So one of the things I often like to do is to sort of capture the outputs in my pip installs on Colab, so I don't have this humongous mess of installation. Okay, so what you can see here is what we were talking about before. This is if you just do word piece tokenization. Oh, sorry, word splitting into words. And now we can have a look at like what the BERT tokenizer does. And there are two ways you can do this in transformers. You can specify the specific class that you want to use for the tokenizer. And this is if you happen to be maybe doing something very specific and you just only want to make sure you get the BERT tokenizer. But the thing that I personally use all the time is just the auto tokenizer, because this will automatically convert the tokenizer into this class anyway. So if I provide a checkpoint and it can identify that, it will then automatically load it this way. Okay, so if we take a tokenizer, it converts the text into these input IDs. But now let's have a look at something here. So why are we doing this twice? Okay. Okay, good. So what we're doing here is we're just taking a sequence of text and then we're extracting the tokens as a list. And so you can see here that in the case of BERT, which uses this word piece tokenization algorithm, the way it distinguishes like words from subwords is using this double hash symbol. So you can see here that in the vocabulary of the BERT tokenizer, it has learned that it's good to split words between trans and everything else. And if we wanted to reconstruct these two words, we just need to know that this double hash means that this former belongs to trans, to build transformer. And so one way you can reconstruct the sentence is you can take your tokens and you can convert them back into input IDs like this. So this will create these IDs. And then you can decode these input IDs to build back the original string like that. Another way you could do this is, let's have a look where we have our inputs. Where are we? Okay, so another way you could do this is if I take my tokenizer and I just tokenize my sequence, then this produces what we saw before. And then what I could do is I could go tokenizer.decode. I put my inputs and my input IDs. And this should return what we saw before. And now you can see the difference between this approach and the one here is we don't have these special tokens. So if you don't want these to be present, I think we can do skip special tokens, true, and then this will give us back the original sequence. Cool, so that's more or less like a sort of deep dive into the tokenizers. Maybe one thing to mention, let's have a look at a different tokenizer so you get an idea of what you might also see. So let's find a GPT model that is not going to blow up the Colab. So GPT-2, let's do maybe this one. So I'm going to just take a tiny GPT. You can also copy the name of the checkpoint, which is quite handy. So we are here. So what I'm going to do is I just want to show you the difference between the GPT model and the way it tokenizes. So hopefully this works. Yeah, so GPT has a kind of very quirky tokenizer where it uses this weird symbol. It's like a G with a little like dot on top of it. And this is what it uses to indicate that there's a white space between this token and this one. So you can see that it's saying, okay, using, and then there's a white space, then R, then there's a white space, and then trans. But then former has no white space. So if we wanted to reconstruct this, we just stitch this back to this. But then there's a white space with a network and so on. And so you can see this is kind of quite different to the BERT one, which basically treats every token as having a corresponding white space unless we have the two hash symbols, whereas GPT-2 is kind of the other way around. It says, assume no, there is no white space unless I put a special symbol like this. Okay, so are there any questions about the tokenizers? Okie dokie. So let's now have a look at how we can handle multiple sequences together. So I'll start the video.
How to batch inputs together. In this video, we'll see how to batch input sequences together. In general, the sentences we want to pass through our model won't all have the same length. Here, we are using the model we saw in the sentiment analysis pipeline and want to classify two sentences. When tokenizing them and mapping each token to its corresponding input IDs, we get two lists of different lengths. Trying to create a tensor or an NumPy array from those two lists will result in an error, because all arrays and tensors should be rectangular. One way to overcome this limit is to make the second sentence the same length as the first by adding a special token as many times as necessary. Another way would be to truncate the first sequence to the length of the second, but we would then lose a lot of information that might be necessary to properly classify the sentence. In general, we only truncate sentences when they are longer than the maximum length the model can handle. The value used to pad the second sentence should not be picked randomly. The model has been pre-trained with a certain padding ID, which you can find in tokenizer.padTokenID. Now that we have padded our sentences, we can make a patch with them. If we pass the two sentences to the model separately and patch together, however, we notice that we don't get the same results for the sentence that is padded. Here, the second one. Is that a bug in the Transformers library? No. If you remember that Transformers models make heavy use of attention layers, this should not come as a total surprise. When computing the contextual representation of each token, the attention layers look at all the other words in the sentence. If you have just the sentence or the sentence with several padding tokens added, it's logical we don't get the same values. To get the same results with or without padding, we need to indicate to the attention layers that they should ignore those padding tokens. This is done by creating an attention mask, a tensor with the same shape as the input IDs, with zeros and ones. Ones indicates the tokens the attention layers should consider in the context, and zeros the tokens they should ignore. Now, passing this attention mask along with the input ID will give us the same results as when we send the two sentences individually to the model. This is all done behind the scenes by the tokenizer when you apply it to several sentences with the flag padding equal true. It will apply the padding with the proper value to the smaller sentences and create the appropriate attention mask.
Okay, so I see we have a couple of questions. So the first question from I Am Holmes. I don't understand why we needed the extra dimension. i.e., based on the error message that is returned, how would you troubleshoot to determine that you needed another dimension? Okay, so I think the best way to look at this is probably with some code. So let's go here and install transformers. Okay, so if I understand the question from Om Holmes, you're talking about this error message. Let's see if it is reproducible. Okay, good. So I think you're talking about this index error that we're getting here. So let's have a look how we might debug this. So the error is saying that the dimension is out of range and we expected to be in the range -1 to 0 but got 1. So let's have a look at what the shape of our inputs are. This is sort of how I would debug this message. So, okay, so we can see that the input IDs have a size of just 14, and that's just representing the 14 tokens that we get when we tokenize the sequence. So I'm going to show you a dirty secret of how most software engineers debug stuff. So you take this and you chuck it into Google, and then you go, this looks like a PyTorch error. And then we have a look and we see if someone can explain what's going on. So you can see some message, someone has a thing here, you're getting some dimension out of range error. And then, okay, this looks like it's like a deeper issue in PyTorch. Maybe that's not so helpful. But then maybe let's look at Stack Overflow. This is often where you'll find a good answer. So someone is getting the same kind of error, and let's see what someone told them in the answer. So they're saying that you're giving a 1D tensor to this thing, but it expects this kind of object. So let's see if that is kind of relevant to what we're doing. So if we look at the error here, it's saying that at some point in the stack trace, we tried to compute a sequence length by taking the size of the input IDs. And then we actually tried to access the second dimension of the input IDs. And so if you look at the size that we provide, it only has one dimension. So basically I can access size 0 because that's the first dimension that's available. I don't know why Colab is so slow. However, if I try to access the second dimension of a one-dimensional object, then that's not possible. So it's going to throw this kind of error. For some reason, Colab is acting really slowly. I'm just going to restart it. Let's see if we can do that. Oh, interesting. So let's see, is it printed? Ah, interesting. So Colab, okay. Let's see. Can I spin up Colab again? Maybe I have too many Colabs open. Okay, let's try again. So I'm going to install this. Okay, fingers crossed this works. Sorry for this. Okay, good. So we're trying to debug this error, and we see that the stack trace is telling us it's here. And the problem is that we're trying to determine the size, or basically we're trying to pick out the size of the dimension in the second component of the input IDs. But the problem that we have is that the input IDs only have one dimension. So their size like that, 14. And if we access the first element, we get 14. That's good. But if we access the second, we're going to get the same error. And so here we're seeing that the problem is that we need to basically provide a batch dimension, which says that we're dealing with one sentence, which has a sequence of length 14. So basically most of the inputs, the input IDs, should have shape, batch size, and then sequence length. Does that answer the question, Holmes? I think that was a bit of a convoluted way of debugging it, but that's more or less how I would do it. Cool. So then there's another question from SRM Suima about can we modify the padding technique? So the answer is yes. And let's have a look where we do padding. Okay, I'm gonna just make this up. Okay, so let's have a look. So I've got a tokenizer, and if I just take a sequence like this, I'm going to get these input IDs. And so then the question might be, if I add some padding, then what's going to happen to my input IDs? So basically, this should, I think, just in this case, provide no padding tokens. So what I'm going to do is I'm going to create two sequences. So my dog is called Fido, and then another sequence which is like my cat is called something really cool, like I don't know, Eliza. So now I've got these two sequences, one is shorter than the other. So now if I pass these to my tokenizer with the padding true, you can see that what happens is in the first sequence, it takes the normal tokens and then it adds a bunch of zeros. to the end. And the number of tokens it adds is just designed so that it matches the same length as the longest sequence in the inputs. Now, the question is kind of like, what strategy can we do to do that? And let's see, I think we can do. So what I'm going to do to find the actual argument I need is I'm going to go to transformers, and I'm going to look at padding, because I can't remember how I pad on the left. So this maybe is it. Padding arguments for pre-trained. So look at the source code. Okay. So I can do longest max length. Interesting. So, okay, that only will give us the options. For example, if I do max length, then this will pad to the maximum length of the whole model. So the model, which is BERT, can process 512 tokens. And so this will process, whoa, huge number of zeros all the way out to the length of 512. And the other option that we have here is longest, which is the default of just the longest example in the inputs. But let's see, how do we pad to the left? I remember we can do this. Okay, so let's see, so we can take in the input padding strategy and pad to multiple of, I was I was pretty sure that I can pad on both sides. So let's see. Thanks. Omar has the answer. Great. So then we can do this. We do padding true and then padding side equals left. Interesting. Did I do it wrong? Maybe it's only for some tokenizers that we can do this. Okay, so padding side. So here we can see that there are default values to pad should be right or left. And this is for the pre-trained tokenizer. Interesting. Okay, let's do this. So let's see. Sorry for this live hacking. So let's have a look. If we look at one of the attributes of the tokenizer, it's called padding side. And here by default, it's right. So I can override this attribute by saying make it left. So it's not a keyword argument, it's an attribute of the tokenizer. That's what I was missing. And so now you can see indeed that we can pad to the left. So I think that should answer the question from SRM Swimmer. Thanks, Omar, for the help with that. Thanks, DK Crazy Div. You see what it's really like in the real world. All right, so let's see. So the question, follow-up question is, will it have an impact on the attention mechanism? Okay, that's a really good question. So the reason we have, so there are two things going on here. So on the one hand, there's the padding, which we need to do so that we can make sure all the inputs are basically a rectangular array. And that's just the way that we need to do things like matrix multiplication in the network. And so once we introduce padding, we introduce the problem that Sylvain mentioned in the video, which is that the attention mask, the attention in general will attend to every single token in the input. So, in this case here, every single one of these zeros in principle is a token which has its own embedding, And then when we calculate attention, we basically do a pairwise multiplication of every token with every other token in the sequence. And that would be a problem because this would sort of say to the model, hey, I've got these 3 tokens, they seem to be related to each other. And then when I construct my kind of representation at the end of the encoder, this would have this kind of like artificial like information from padding. And we don't really want that because, you know, padding was something we just artificially injected. And so the thing that Sylvain mentioned is that we will get in general something called an attention mask. So I'm going to just call this my tokenized, well, let's call this inputs. So if I look at my inputs, I've got input IDs and I've got an attention mask. And this attention mask will then, when we compute the attention inside BERT, it will say every time you see a 0, completely ignore that token. And so what you can see is that the tokenizer has correctly figured out that if I say pad on the left, then make sure that there's a mask for the first 3 elements or the first 3 padding tokens. So these zeros will basically will say to BERT, ignore this when you compute attention, just compute attention on the actual words we care about. So to answer your question, Esram Pluma, it doesn't have an impact because the attention mask takes care of that, and it's all done automatically through the tokenizer. Thanks, I.M. Holmes. That's very kind. I'm doing one next week, so I think for session 3, you can come join. Okay, so let's see. Let's maybe have a look at, I think, one of the last sections we have here, putting it all together. So let's see. Yeah, let's walk through a little bit the code of this section. So this is going to kind of bring together all the things that we've learnt in this session. And I'm going to just go through the code. So the idea, just to remember what we're doing in this chapter, we're kind of deconstructing the pipeline, looking at all the pieces that go into it. And now we're going to sort of put this all together to sort of have our own custom pipeline. So first thing, we just load a checkpoint, a tokenizer, and feed some inputs. And in fact, I'm going to do this one here, which now produces with 2 sequences. And so now we can have a look at the different sort of ways that we could pad. So this is, I think we saw this before, the model inputs now are going to have padding tokens that go all the way, they match the longest in the sequence. So in this case, this is the longest input. So the first one doesn't get any padding tokens, but the second guy gets all these extra zeros here. And as we saw before, the attention mask will get all these extra zeros to say, don't pay attention to those tokens. Then, as we saw before, we can put max length, and then this will, let's see, this will now put a bazillion zeros on top of everything. So all these zeros we saw. So this goes up to 512 extra zeros for the BERT max length. And then you can also configure how far you want to add padding to if you want to. The other thing I didn't really mention so far is this concept of truncation. So let's have a look at how that could work. So basically what will happen most of the time in unless you're dealing with like tweets or, very short texts, a lot of the time your inputs will exceed the maximum length that the transformer can process. And so this is actually one of the main challenges with transformers, is that they're really good at kind of short to medium length inputs generally. But as we go to very long sequences, there's 2 problems. One is that attention is very computationally intensive and expensive to do. And the second is that most of the models just predefine what is the maximum length that the input can have in the pre-training phase. And once you define that, you can't exceed it. So in this case, I want to show you what would happen if we did that. So I'm going to take a sequence. and I'm going to say, I don't know, let's take this guy. And I'm going to try and break BERT. So I'm going to times this. What's this? This is probably 14 tokens. Let's times it by 1,000. So now I've got a really long sequence. And I want to see what happens if I try to pass this sequence to my tokenizer. Just, if I just did nothing, what would happen? Okay, so now what you can see is that we get a warning. The token index sequence length is longer than the maximum sequence length of this model. Where's the message? So it's saying that we've got, way more tokens than we have. And then you go, oh, okay, I don't care about warnings. So I'm going to just say, who cares? And I'm going to try and return tensors. Okay, so this seems to work. And now what happens if I take a, do we have a model? No. Okay, so from transformers, import auto model. And now what happens if I try to, do we have a checkpoint? Where's my checkpoint? Yes, I do have a checkpoint, good. Let's try to load my model. So what I'm trying to do here is I want to show you what happens if we just naively try to pass a 14,000 long sequence to BERT. And so now, if I'm not mistaken, our inputs should break the model. Indeed. So here we can see we've got an index error. The index error is out of range. And that is essentially trying to say to us, look, you tried to do this embedding operation somewhere in the code, and you are trying to pass an input which violates the constraints set by the model. And so this is an example where, we just broke the model because we gave it something that was too long. The solution to that is to use the truncation parameter and set it to true. And what this will do is this will now take our inputs and truncate them. So let's get the input IDs and then the size. And this will now, this has now converted them to the maximum size of the model, or truncated them to the maximum size. And so now I can feed this to my model and it's happy. So this is one way you can deal with the problem of when your text is too long. You can just truncate it. And my experience is generally that truncation works okay for like classification tasks. So if you're doing like, multi-class or type this kind of thing, generally like a lot of the information is actually at the start of the review or the tweet. But you don't want to do this for things like question answering because the answer might be somewhere towards the end of the text, and then if you truncate it, you lose it. And we'll probably see later on in another iteration of the course how you handle that. And also in summarization, it's a little bit depends on the case. Sometimes I've been able to truncate and get okay results, but sometimes you have to do clever things like split the text into different pieces, truncate those pieces, and then kind of aggregate the results. Okay, so that's truncation and padding. And yeah, I think that's pretty much what we need to do for this. So are there any questions at this stage? Okay, so one thing I would like to mention is you've probably seen we have the forums, and on the forums we have a course category. So if you have any questions that come to mind after this session, or just questions in general about transformers, you can ask them here and one of us will respond. I think a really cool thing to do if you have the time is to share your projects. So in fact, we can see DK Crazy Div here sharing his awesome data set from the Model Hub. And as you start learning transformers, a really cool way to sort of get some feedback on how you're going is to kind of share your work. And at least for me personally, I come from a non-computer science background. I studied physics and then decided to switch into machine learning. For me, this kind of sharing was a very powerful way of getting some feedback from the community and also trying to learn how to communicate, which is a really important part of doing any data science in the real world or in general. So, for example, a cool experiment would be this one that was asked today of like, what happens if I change the config of the model? Does it break things? That would be a cool thing to show. Or in general, like, any sort of training experiments you do would be awesome to share. Okay, there's one last question from Resh Mashake. How to check the default model? Okay, so let's have a look at this. Okay, so let's take a pipeline. So I probably need to go from transformers, import pipeline, and then I'm going to create a pipeline for sentiment analysis, for example. So the question is, how do we check what model is being used? So the pipeline object, it has a bunch of different attributes, and the attribute that is interesting is the model in this case. So if we look at this, it's going to tell us, okay, it's like some output, but maybe we can just look at the config of the model. And then we can see that in this case, the model that we're using for sentiment analysis by default is Distilbert, and it's this checkpoint that we saw earlier in the class. So I hope that answers the question, Resh Mashake. You can do this for any other pipeline. Let's have a quick look. What happens if I do question answering? So the default model in question answering is going to be Distilbert base case on squad. So that's the one we have. Cool. So there's another question. Are the recordings available for session 1 from Sylvain? I was not able to find it on the YouTube channel. I believe they will be, but I guess I'll have to check with Sylvain later. I'm pretty sure we try to put everything on YouTube that we can. So I'll let you know when it's up. So yeah, thanks a lot for your really cool questions. It's a real pleasure having people interact. Otherwise, I would just be talking to the screen by myself. So thanks for your input, and we'll see you for the next session. So Sylvain is giving the session tomorrow, which is the same one as today, and next week we kick off with chapter 3.